Hello students, today we are going to the subject electromagnetic field theory. Myself, Rajasekaran, Associate Professor of Electrical Department. So in electromagnetic field theory, the various topics we are going to discuss are the introduction about the algebra about the vectors. Normally we are going to see the coordinate system, Cartesian coordinate system, cylindrical coordinate system and spherical coordinates system. So why we are studying these three systems, Cartesian, cylindrical as well as the spherical coordinate systems, are the electromagnetic field is a three-dimensional field. So in order to evaluate the electromagnetic fields, calculation of various parameters and going to analyze the electromagnetic fields, we are in need of these three coordinate systems. So in that aspect we are going to in detail analyze the three coordinate systems as an application point of view. Then we have the various theorems normally involved in the mathematics, divergence theorem and Stokes theorem. These are the topics in unit 1. In unit 2, electrostatics. Electrostatics is a study of the electric field, the origin of the electrostatic field. So in this we are going to discuss about Coulomb's law, force between two charges and electric field intensity, potential difference, electrical flux and flux density. So as a law we are going to see about the Gauss law. Third unit is about magnetostatics. It's a study of magnetostatic field. So in which as like as in the Coulomb's law of electrostatics, here we are going to study about the Biot-Savart law, the force between, it is telling the force between two current carrying conductors. So analogous to the electrostatic field, the topic electric field intensity, here we are going to see the magnetic field intensity due to the current carrying conductor. As Gauss law in electrostatics, here we have the Ampere's law, Ampere's circuital law. So like electric potential, here magnetic potential and magnetic vector potential. Fourth unit is dealing with electric and magnetic fields in materials. So normally materials are capacitor and inductor. Electrostatic material is capacitor, magnetostatic material is inductor. So studying how to find inductance and capacitance for various materials, various regular materials, we are going to calculate the inductance as well as capacitance. And then Poisson's and Laplace equations, they are using as an analyzing tool for the magnetic field finding and electric field finding in materials. And boundary conditions for electrostatic and also magnetostatics with some simple examples. So that's all about electric and magnetic fields in materials. Next, electrodynamic fields and electromagnetic waves. Electrodynamic fields. So normally we are dealing electromagnetic field as a static one, but in general they are dynamic fields. So as a dynamic one, we are going to see about the originality of the electromagnetic fields. So in which we are going to see about the electromagnetic waves. So they are propagating as a wave only. They are transforming the energy in various electromagnetic parameters. So here we are going to analyze the electromagnetic field as a wave with various wave parameters, and also the Maxwell's equations. Maxwell's equations are differential integral equations, so which are used for analyzing the electromagnetic wave parameters. So in that aspect, Maxwell's equation, then pointing theorem, and also various wave parameters for various cases. So that's all about electrodynamic fields and electromagnetic waves. Okay, introducing. So electrostatics is the branch of electromagnetics dealing with the effects of electric charges at rest. So only we are dealing the field produced by the charge at rest positions. So that is the study of electrostatics. The fundamental law of electrostatics is Coulomb's law. So it deals with the force between two charges. So electromagnetic is everywhere. So here we are going to deal about the charge. So charge is the infinitesimal particle of the universe, the whole universe. So we can say electromagnetic is a fundamental to the advancement of electrical and computer engineering technology. So it is dealing with the infinitesimal particle charge. The field produced by charge is electric field, and the field produced by the moving charge is magnetic field. Examples for some electromagnetic applications. So from normal small mobiles to various satellite communications, it's a magnanimous materials, all are involving the application of electromagnetic fields. All communication involving in satellite, various computers, various receiver, antenna propagation materials, involving the solar energy production, ship applications, rocket launching. So everywhere we have the applications of electromagnetic fields, and also analyzing. So even our cells are made up of charges. So study of electromagnetic fields of a human body is also equally appreciated. So as we discussed, electromagnetic field is a three-dimensional. So these are governed by partial differential equations. So for analyzing these electromagnetic fields, so we are using the coordinate system, the three-dimensional coordinate system. Electrostatics, study of charges at rest. Magnetostatics, charges, flowing charges, creating magnetic fields. So it's a study of charges in steady motion. Electrodynamics, charges are in time varying motions. So normally, practically we have the time varying motion of charges. So what is charge? A fundamental conserved property of some subatomic particles. So we have in atoms are fundamental for any type of material, solids, gaseous, as well as liquid materials. So in each atom we have the subatomic particles known as electron, proton, neutron. So are charges. So electron negatively charged, proton positively charged, and neutron chargeless charge. So the electron's charge is 1.602 into 10 power minus 19 coulomb. So for constituting 1 coulomb charge, we need 6.24 into 10 power 18 electrons. 1 coulomb charge. In 1 coulomb charge, we have 6.24 into 10 power 18 electrons. Charge is conserved. It is obeying the energy principle, energy conservation principle. Scalar and vector fields. Scalar field is a function that gives us a single value of some variable for every point in space. So only dealing with the magnitude, it's a scalar quantity. So normally the voltage quantity, current quantity, energy, temperature. So they are giving only the magnitude of these parameters, not mentioning any other. So that field are scalar fields. The vector is a quantity which has both magnitude and a direction in space. Velocity. So velocity is not only giving the details about the speed and also the direction of the object involved, and also momentum, acceleration, force. So these are all vector quantities. So in electromagnetic fields we have electrostatic field intensity, magnetostatic field intensity. So all are under vector quantity. So analyzing the electromagnetic fields we need the fundamentals of vectors. So examples for the scalar fields. So only giving the magnitudes, temperature, vector fields, magnitude as well as direction. So these arrows are indicating the direction of the quantities, whatever it may be. It may be velocity, fluid particles moving, circulating flow of particles. So all are vector quantities. So the gravitational field points towards to the center of the earth. So all are having both the magnitude as well as the direction. The magnetics having north and south poles. So they are having the electromagnetic fluxes showing the direction north to south. The Earth's magnetic field behaves as if there were a bar magnet in it. So we can consider this Earth as a magnet having north and south poles. So having the magnetic waves from north to south. So giving both the magnitude as well as the direction. Unit vector. So for analyzing the vector fields, we need to study about the unit vector. So unit vector is a vector of magnitude 1. And also for making any scalar into vector, we are multiplying the scalar value with the unit vector. By multiplying the scalar value with the unit vector, we can get the vector quantity of that particular scalar. For transforming any scalar into vector, we have to multiply the scalar magnitude with a unit vector. So vector components, the magnitudes of vector components, and also angle between the two vectors. So considering A and B as a two vectors, we can find the angle between the two vectors, tan inverse of B by A. Dot product of two vectors A dot B, and the cross product between any two vectors A cross B. So one is the scalar product, other one is the vector product. So A dot B. Mathematically, how to calculate the dot product between two vectors? A dot B is the modulus of A multiplied by modulus of B, and also the angle between the two vectors, the cosine value of the angle between the two vectors. So they are obeying the two various laws, commutative laws. A dot B equal to B dot A, as well as the distributive law A dot B plus C is equal to A dot B plus A dot C. And the dot product between any two vectors, AX dot AY, AY dot AZ, AZ dot AY. So they are the two vectors perpendicular to each other. So the angle between the two vectors are 90 degree. So cos 90, taking the value of 0, the total dot product between any two vectors AX, AY, AY, AZ, AZ, AY are all 0. And the scalar product of the two making dot product between the same vectors AX dot AX, AY dot AY, AZ dot AZ. So the angle between the same unit vector, the angle is 0. So taking that, cos 0 is 1. So the dot product value is 1. Cross products. So cross products. So for multiplying any two vectors in cross products, so we are using a matrix. So finding the determinant of 3 rows 3 column matrix, we can find the cross product between any two vectors. So A cross B is represented by one matrix that is 3 cross 3 matrix. So why these 3 means, we are mentioning here the 3 coordinates x, y and z coordinates. The first row representing the unit vectors AX, AY and AZ, So they are all unit vectors. Second row representing the coordinates of the vector values of the first vector. So here the vector A. The second vector B is represented in third row. Bx, By and Bz are the third coordinates of vector B. So finding the determinant of this matrix, we can get the cross product between two vectors A and B. So properties of cross products. It is not commutative as well as like in dot product. So where A dot B equal to B dot A, but it is not in the case of cross products. A cross B not equal to B cross A, because A cross B is opposite to B cross A and anti-commutative. You can say it as anti-commutative. A cross B is equal to minus of B cross A. It is not associative. A cross B cross A not equal to A cross B cross A, but in the case of dot product they are associative, and it is distributive. A cross B cross A is equal to A cross B plus A cross C. Then scalar triple product A dot B cross A is equal to B dot C cross A and C dot A cross B. So A dot B cross A is a scalar triple product. So having no direction, only with the magnitudes, so we can say it as a scalar triple product. But it is not giving. So when the R by making vector triple product, we are not getting the scalar value. So they are producing the vector values. A cross B cross A gives B into A dot C minus C into A dot B. So they are giving the vector values. So representing the vector system, we are using three primary coordinate system: rectangular, cylindrical and spherical system. Rectangular may be known as in another name called Cartesian coordinate system. So rectangular sheet representation is representing the rectangular system. Wires or cables they are mentioning using by cylindrical system, and spheres we are using the spherical coordinate system. So three types of coordinate system: rectangular, spherical and cylindrical coordinate system. The parameter involved in rectangular coordinate systems are x, y and z. So having all as a length parameters x, y and z, that is rectangular coordinate system. Spherical coordinate system r, theta and phi, where r is a length parameter, theta and phi are the angular parameters. Cylindrical coordinates, they are r, phi and z. So r and z are, z is the height of the cylinder, r is the radius of the cylinder and phi the angle. So two length parameters with one angular parameters, we can represent cylindrical coordinates. We can transform one coordinate of system into another coordinates of system. Normally we can transform the Cartesian to spherical, spherical to Cartesian, or Cartesian to cylindrical, cylindrical to Cartesian, or in between cylindrical and spherical, spherical to cylindrical and cylindrical to spherical. In whatever form we can transform from one coordinate system into the other one. Rectangular coordinates, we have x, y and z parameters. The limit of x is minus infinity to plus infinity. Similarly, y and z parameters also from minus infinity to plus infinity. Cylindrical coordinate system, we have the parameters r, phi and z. So r is the limitation from 0 to infinity, phi is 0 to 360, r 0 to 2 pi. The z is the height of the cylinder. It is minus infinity to plus infinity. Spherical coordinates, the coordinates are r, phi, theta. So where r is 0 to infinity. So starting from the origin, it is from 0 to infinity. Phi is from 0 to 2 pi, as well as in the case of cylindrical coordinate system. but theta is from 0 to 180 degree. So theta is the angle between the radius of the sphere making with the z axis. So that is the angle theta. So it is varying from 0 to 180. Then how to convert one system into another system? So we can convert the parameters, the vectors from one form to another, one system to another system. Rho is equal to, the rho is the parameters of cylindrical. So that can be related with the Cartesian parameter x and y. Rho is equal to root of x square plus y square. And the x can be related with the cylindrical parameter rho and phi. X is equal to rho cos phi. Phi, the parameter in cylindrical as well as in spherical. Phi is tan inverse of y by x, and y is equal to rho sin phi y. Then z used in Cartesian as well as cylindrical, they are same in both the cases. Then vectors, in vector form, so points we have related. In vector also we can relate any two system. Ux is a vector in Cartesian, uy the vector in Cartesian, uz the vector in Cartesian. We can convert, we can transform into, we can find ux, uy, uz from the cylindrical parameters. So ux is equal to cos phi u phi minus sin phi u phi. Uy is this sin phi u rho minus cos phi u phi. Uz is uz. So both are same in both the system. Then similarly we can find the cylindrical vectors u rho, u phi and uz from the Cartesian vectors ux, uy and uz. It's a general formula for finding the Cartesian vectors ux, uy, uz from the cylindrical known vectors u rho, u phi and uz. Next, the relation between spherical and Cartesian coordinates. So R is a spherical points. We can find R by using the Cartesian parameters x, y, z. R equal to root of x square plus y square plus z square. And x can be found from the spherical coordinates. X is equal to r sin theta and cos phi. Then theta the spherical parameters. Spherical parameters can be found from the Cartesian parameters. Theta equal to tan inverse of root of x square plus y square by z. And the Cartesian parameter y can be calculated from the spherical parameters r theta phi. Y is equal to r sin theta sin phi. Phi, as the case in previous, phi is equal to tan inverse of y by x. Then z equal to r cos theta. So problems finding the angle between two vectors. So by using the dot or cross product we can find the angle between any two vectors. Then area integrals giving the area. So involved in two-dimensional parameter dx and dy. So example, we can find the area of the representing dx and dy. Multiplying dx and dy, we can get the area of integrals. Area is equal to, so integrating dy dx from their limits, upper and lower limits, we can find the area. So here z is constant. So only we are having two variables in x and y, and having z as a constant, we can find the area involving y and the x axis. The scalar product, surface integral. The surface integral is a two-dimensional integral. Differential surface element. Vector is normal to surface. So dx is equal to dx dy, and the unit vector perpendicular to both dx and dy, that is az. Differentials for integrals. examples for line differentials. dl equal to dx into ax, where dx is the small elemental length in x-axis multiplied by the unit vector in x-axis, that is ax, or dl dr into ar, or dl r d phi into a phi. So r d phi is the length parameter in cylindrical, that is r d phi with the unit vector a phi. Surface null examples, ds, so area, giving area ds is equal to dx dy, and a unit vector perpendicular to both x and y, that is az. Then r d phi into dz, then with the unit vector ar, the third vector, which is perpendicular to both phi and z. For volumes, dv, dx dy and dz, involving all the differential parameters in three directions, x, y and z. So phi of x, y, z is a differentiable scalar field. So we can find gradient. So gradient of phi is equal to the differential of the phi is giving the gradient of that vector phi. So gradient of phi is a vector giving a differential value of the flux distribution. So divergence of vector, any vector can be found del dot dA. So by having the dot product with any vector with del operator, we can get divergence of that vector. So gradient, next one is divergence. So divergence of any vector, is, so here we have the dot product between two vectors. So divergence of any vector is a scalar value. Is a scalar value. Divergence of any vector is a scalar. So divergence B, del dot B, that can be represented by dou V by dou x by dou x, dou Vy by dou y, dou Vz by dou z. So the differential operation of the vector fields giving the divergence. So del phi is equal to del square phi, that is divergence of gradient phi. So divergence of a triple partial difference, double partial differentiation. So that is called scalar Laplacian. Similarly, vector Laplacian is a differentiable vector field. Differential operators. So using differential operation, we can find gradient, divergence, curl, and also Laplacian for any vectors. So gradient is a vector. So gradient of any field, so it is a vector. But divergence is a scalar. So having dot product between two vector operations, so it is giving a scalar value. The curl is a vector. So having the cross product between any two vectors, it is giving the vector. So gradient is a scalar field, divergence is a vector field, curl is a vector field. Definition del phi is equal to del dot V. Gradient is del phi, divergence is del dot V. Curl of vector V is del cross V. Laplacian form is del square phi. So here we are using the Gauss divergence theorem. Del dot A is equal to divergence of A. So using which we can find the charge density, and also we can relate the surface integral with the volume integral. Stokes theorem is giving the relation between line integration and surface integration. Gauss divergence theorem relating the surface integral and volume integral. So for our convenience, we can transform surface into volume or volume into surface, then line into surface or surface into line integral. In any form we can use. So for the purpose of transformation, we are using the Stokes theorem and the Gauss divergence theorem. So it's a cross product between. So what is the physical meaning of the curl? Second unit, electrostatics. is a branch of electromagnetics dealing with the effects of electric charges at rest. So only we have the charges at rest. Fundamental law of electrostatics is Coulomb's law. The electric charge, electrical phenomena caused by friction are part of our everyday lives and can be understood in terms of electrical charge. So we can feel the charges, the existence of charges. So by rubbing any two objects or our hands, we can feel the existence of charge. The effects of electrical charge can be observed in the attraction or repulsion of various objects when charged. When charged, there is a force between any two charges. It may be attractive or repulsive. Charge comes in two varieties called positive and negative. So these forces are termed as positive as well as negative. Objects carrying a net positive charge attract those carrying a net negative charge and repel those carrying a net positive charge. So in simple, so we can say like charges are attracted and unlike charges are repelled from each other. Electron. So electron charge value is 1.602 into 10 to the minus 19 coulomb. Such a very less coulombic particle electron is. So charges, positive charges, the flow of positive in surface as well as volume. Point charge is of coulombs. Line charge are represented in coulomb per meter. It is single dimensional. Surface charge coulomb per meter square as a two dimensional one. Then volume charge is measured in terms of coulomb per meter cube, being as a three dimensional one. Electrostatic force. The electrostatic force is nothing but the force by one charge on another 1 coulomb charge. So that force is called electrostatic force. Force between any two particles due to existing charge is known as electrostatic force. Here, any one of the charges is of 1 coulomb. And the various parameters involved in electrostatic force. Permittivity. So permittivity is epsilon naught. Epsilon naught is the permittivity of free space. Its value is 8.85 into 10 to the minus 12 farad per meters. Then relative permittivity ER, epsilon r. So absolute permittivity is calculated as the product between the two, permittivity of free space epsilon naught and the relative permittivity epsilon r. Coulomb's law. Coulomb's law states that force between two charges, and also in giving a mathematical formula for find out the force between any two charges. So here F12 is a constant K into the product of the two charges Q1 and Q2 by the distance between the two vectors, that is R12, squaring that the distance between the two vectors. F12 is K into Q1 Q2 by R square. So K, the value of K is, so it is 1 by 4 by epsilon naught. The value is 9 into 10 to the power 9 Newton meter square per coulomb square. So value of the K, 1 by 4 by epsilon naught. So the force may be attractive or repulsive. So F12 is 1 by 4 by epsilon naught Q1 Q2 by R12 square. Faraday, beginning in 1830s, was the leader in developing idea of electric field. Here's the idea: a charged particle emanates a field into all space. So here a charged particle colored by blue. So it is radiating the field into all space. In all direction it is emanating. Another charged particle senses the field and knows that the first one is there. So there is a force between any nearby charges. F12 is the force between charge 1 and 2. 1, 3 is the force between 1 and 3. So every charge is making force with the nearby charges. They may be attractive or repelling according to the magnitudes. We define the electric field by the force it exerts on the test charge Q. So as already said, electric field energy is the force exerted by one charge on another 1 coulomb charge. So it is force divided by the magnitude of the charge F by Q, and F is equal to Q into E. Vector F is equal to Q multiplied with the vector E. In test charge is too big, it perturbs the electric field. So the correct definition is for electric field or electric field intensity, E is equal to limitations Q tends to 0 F by Q naught. So the unit for electric field energy is Newton per coulomb. So force on 1 coulomb charge, so it is Newton per coulomb. Or in another word, it is volt per meter. So later we are going to see what is 1 volt. So electric field energy is force exerted by the charge on a unit charge to the charge of the unit charge. So like the force equation, F is equal to mass into acceleration. Here it is, so instead mass, here we are substituting Q. Instead acceleration, we are substituting the vector E, electric field intensity. Electric field due to small charge, electric field intensity, del E, that can be found by using this formula 1 by 4 by epsilon naught the constant K del Q, the small elemental charge value by R square, then multiplied with the unit vector. So the electric field at any point is E 1 by 4 by epsilon naught into the unit vector r cap into lambda x of dx by r square. So integrating this, we can get the real value of electric field intensity. Then area charge distribution and also line charge distribution and volume charge distribution. For that case also we can find the electric field intensity. So by finding the small elemental charge elemental, we can find the electric field intensity. Then by integrating it, we can get the total value of E. So charge distribution along a line, charge distributed over a surface and inside a volume, we can find electric field intensity. With some examples, we can find the charge distribution and the electric field intensity. And also we can find a ring of radius A. For that ring of radius A, we can find the electric field intensity. By finding dE, then integrating it, we can find the total electric field intensity. For derivation, for finding electric field intensity for a radius, for a disk of radius E. Similarly, for any infinite plane sheet, we can find the electric field intensity. Or is the application of the Coulomb's law in determining the electric field intensity for various line and also surface material. Electric flux. Using Gauss law, we can define electric flux. What is electric flux? The electric field lines are considered as electric flux. Electric field lines passing through a surface, and use this count to determine the electric field. The flux lines, the electric flux lines is nothing but the electric field. So flux is equal to E into A, where A represents the area. The surface is touched, fewer lines cut the surface. Flux, electric flux distribution. Gauss law and making a Gaussian surface, we can determine the electric field for these various Gaussian type surfaces. These are all the applications of Gauss law in determining various electric field intensity cases. So Gauss law, integral of E dot d is equal to the charge q by inside charge divided by the permittivity epsilon naught. So these are all applications of the Gauss law in determining electric field intensities. Next one, electric potential. So from electric field intensity we can find electric potential. So electric field intensity here given by E, vector E is equal to limit Q naught tends to 0, F naught by Q naught, where E is electric field intensity, Q naught is a small point charge value, F naught is the force between any two charges. So similarly it is useful to define the potential of a charge in terms of potential energy of a test charge Q. So test charge Q, its potential is limit Q naught tends to 0, U of R by Q naught. So where U of R is the work done removing the test charge. So that is 1 by 4 pi epsilon naught Q naught by R. So potential of R equal to 1 by 4 pi epsilon naught into Q by R, where Q naught is 1. So it is Q by R. The electric potential difference between 2 points A and B. So like deriving potential, here we can find the potential difference between 2 points. So del V is the potential difference between 2 points. So del U by Q naught, del U can be found by integrating F from the limit RA to RB, then dividing by Q naught, we are getting the integral of E dl. So in this way we can relate the potential difference and electric field intensity. The electric potential and electric potential energy are related but not the same, because potential is the work done to move a unit positive charge. So potential unit is 1 volt. So 1 volt, how we derive 1 volt? It is nothing but to bring a unit positive charge to a particular point. For any point we can define the potential. For any point, suppose we are having a point, for that point we have to determine the potential at a point. The potential at a point is nothing but the work done to move a unit positive charge, a 1 coulomb charge from infinity to that particular point is the potential of that point. So its unit is joule per coulomb. 1 joule per coulomb can be also termed as 1 volt. So the potential difference is related with the electric field intensity. So finding potential using the formulas we derived, we can find for any point the potential value. And also we can find the electric field intensity. Since it is related with the potential, we can find the electric field intensity from this. And also electric potential, we can calculate electric potential for any radius or any ring of radius R, and a disk of radius for surface material disk of radius R. Also we can find the potential. So that's all about electrostatics. The next unit is magnetostatics. So dealing with the magnetic fields produced by the moving charges. So as well as Coulomb's law, here we are substituting Biot-Savart law. So Biot-Savart's law giving the force between any two current carrying conductors. So current carrying conductor is a source for magnetic fields, using which the magnetic flux density between any two current carrying conductor or any current carrying conductor is given by dB, that is mu naught I by 4 pi I into dx by r cube. So where I dx is a current element, current multiplied by the small elemental length. So using this we can find the magnetic field for any straight line. As like as in Coulomb's law, here we are substituting the Bayes-Savart law. And as substitution for Gauss law, here we are using Ampere's law. So Bayes-Savart law, dB is mu I by 4 pi divided by r cube, where mu naught is 4 pi into 10 power minus 7. This permeability of the material. Current carrying conductor, the current element dI. For any distance x, we are finding dB. We can find magnetic field due to a straight wire. Magnetic field of infinite straight wire. So using Bayes-Savart's law and Ampere's law, we can find electric magnetic flux density for the current carrying. So here we are finding the magnetic flux density for any current carrying conductor at a distance r. B is derived as mu naught I by 2 pi r. The magnetic flux density is mu naught I, that mu naught is the permeability, I is the current carried, r is the distance. It's parallel current carrying conductors. So two parallel conductors carrying current IA and IB separated by a distance. We can find the force or flux density. So here BA, the flux density by A, the current carrying conductor A is mu naught IA by 2 pi d. The FB, so force on B, we can find. So by having a cross product with the current element, we can find the force. Similarly, the field due to B, BB is also mu naught IB by 2 pi d. The force is calculated. So here we are using the magnetic flux density. Integral of magnetic flux density is giving the flux. Surface integral of magnetic flux density giving magnetic flux, that is equal to mu naught I. So for cylindrical wire, we can find the magnetic flux density B. So by calculating B, we can also find the magnetic field density H using the relation. So B is equal to mu naught H for solenoid. We can find. So for a solenoid, for having various loops, we can find the total magnetic flux density. Similarly for a toroid. So electromagnetic force. So it's a combination of electric as well as magnetic fields. So Lorentz derived a force in the combination of electric as well as magnetic. So in that way, F is equal to Q into Q is the magnitude of charges, E electric field density concerning the electric field, plus U cross B. U cross B, B is the magnetic flux density cross U. So it is the combination of electric force and magnetic force. Okay, scalar magnetic potential, like electric scalar potential, here we have scalar magnetic potential. So that is H is equal to minus del of Vm, and del square Vm is 0 using Laplace equation. A scalar as well as vector potential. Then magnetic forces and torques, finding magnetic forces and torques. So from forces, how to find the torque. So two forces are the same magnitude, you can find the force is, so torque is R cross F. So R, the distance between the two. You can find the net torque from the force. So fourth unit, electric and magnetic fields in materials. So here as a materials, we have capacitor and inductor. Capacitor is the electric field material and the inductor is a magnetic field material. So using, we are going to use Laplace and Poisson's equations. So by solving these Laplace equations for various system, the electric field lines surrounding a charges at rest, electric field lines. So you can find the electric field chemistry. Then capacitor is electrostatic material. Capacitor is basically two parallel conducting plates with the air or insulating material in between. So two conductors separated by some dielectric media is defined as a capacitor. Symbol representing capacitor. So it is defined with the battery. And a capacitor is connected to an external potential charge flow. So as a source, it will supply. Capacitors are also very good at releasing their stored charge all at once. The capacitors in your tube and TV are so good at storing energy that touching the two terminals at the same time can be fatal, even though the TV may not have been used for months. So it is because of the capacitance present in the television material. Dielectrics. So what is dielectrics? In dielectrics, there are no free charges but bound charges, that is electric dipoles are present. So they are termed as dielectrics. And also carrying charges, there is a torque and also force. Dielectric in static fields. Flux density and dielectric constants for various materials. Boundary conditions. Using boundary conditions, we can calculate capacitance. Then magnetic material. So we have inductor. We have represented inductor as a magnetic materials. So current, passing current through coils, we are creating the magnetic fields and magnetic circuits. So inductor is called as the magnetic material. So having self-inductance and mutual inductance, using which we can find inductance for coaxial cable, inductance of toroid. Using various approaches, we can find inductance for various material. And also we are using the Lorentz force. Similarly, we can find energy of an inductor. Not only so by calculating the inductance charges, we can find the total energy, total magnetic energy stored in an inductor. So it is half Li square, half into L into I square, where L is the inductance of that coil, I is the current carried by that inductor. So finally we have electrodynamic fields and electromagnetic waves. So being electromagnetic waves as a propagator, so we have discussed about the various wave parameters and how to solve the electromagnetic wave-like problems using Maxwell's equations. This is all involved in this topic. Induced EMF and Faraday's law induction. So EMF induction, changes in magnetic field creates electromotive force. Similarly, current carrying conductor based on magnetic field experiences a force, rotate coil in magnetic field. Change in current in the loop of creates flux changes and induced EMF is produced. That is generator principle. So induction of electromotive force. Motional EMF. EMF is induced in a conductor moving in a magnetic field. The term introduces 4 ways of producing motional EMF. We will cover the first 2 in this lecture. So moving motional EMF. So how to calculate the motional EMF. And Maxwell's equations. Maxwell's equations give the solution for electromagnetic wave. So it is a partial differential as well as integral equations. By solving these equations, we can find various parameters of electromagnetic waves. So using Faraday, Gauss law, Ampere's law, the equations are derived. So giving relation between the two type fields, electric as well as magnetic fields. So H is magnetic parameter and D is electric parameter. E is electric parameter, B is magnetic parameter, D is electric parameter and rho is charge density. So similarly we can relate electric field as well as magnetic field. By solving integral differential equations we can find various electromagnetic wave parameters. Okay. So Maxwell's equations are the solution method for solving electromagnetic problems in electromagnetic waves. So where the electromagnetic wave is propagating. So it is perpendicular to both the electric as well as magnetic field. It's the direction of the propagation of electromagnetic wave. So it can be represented in electric field intensity as well as magnetic field intensity. So wave equation del square B minus mu naught epsilon rho square B by rho d square equal to 0. The first one is, previous one is for electric field. Del square E minus mu naught E rho square B by rho d square equal to 0. It is for electric field. And for magnetic field, it is del square B minus mu naught epsilon rho square B by rho d square equal to 0. Wave equation with V square equal to, where V square is 1 by mu naught epsilon, the velocity, square of the velocity. So the velocity C is 1 by root of mu naught into epsilon naught. So mu naught is permeability, epsilon naught is permittivity. C is the velocity of light in electromagnetic waves. So various parameters, various wave parameters we can determine by solving these equations. The direction of electromagnetic wave is perpendicular to both electric as well as magnetic fields. So for a good conductor, we can find the various wave parameters. Similarly, velocity dielectrics. For any type of materials, we can find the wave parameters using this by solving these wave equations. And Poynting vector. So Poynting vector is giving the energy on electromagnetic fields. That is the product, the cross product of E and H. By having cross product with electric field density and magnetic field density, we can get the energy transported. Using this Poynting vectors. So in this way, we conclude. The electromagnetic wave field is a fundamental field for any type of electric field applications. So it can be related with the smaller machines to mega type communication. In all the fields, we have the applications of these electromagnetic fields. So by studying these fields, so we can enhance our knowledge the elaboration of the electromagnetic field.